So I've called this next section we're working on superposition, and you'll see why that's true in a little bit. But what we're going to be doing is considering the full problem that we started this set of videos with. That's the non-homogeneous problem. So real quick, I'm just writing out that same right-hand side of the differential equation that we were using before. And I'm going to take it back to, instead of being equal to 0, we have the flexibility of it can be equal to any g. And I'm going to use this kind of swirly thing that's definitely different from a star to denote this different differential equation. So, in order to solve this problem, what we need to have is some function that we'll call y sub p. That needs to satisfy the full ODE that I just wrote out. So you just need to find one thing that when you plug it into that equation, it works. And then you also need the fundamental solutions y1, y2, down through yn to the homogeneous problem that we talked about earlier. Then the general solution to this problem we're talking about now is y equal to y sub p plus c1 y1 plus c2 y2 all the way down through cn yn. So we take the general solution we had before and we just add this new function that works in this new problem we're trying to solve. I'm going to flip the page, so pause if you need to catch up with writing. I'll make a plug for the skeleton notes where a lot of that was already filled out for you. But the reason this works is because they rely on a principle called superposition. Which is that linear combinations of solutions are still going to be solutions after you add them together. So it's actually how that c1y1 plus c2y2 so on and so forth worked for finding general solutions in the homogeneous case as well. And we can use it to solve complex g of x problems. So supposing we had an of x nth derivative of y plus all that stuff, a0 of x, y, equal to some function g that we can represent as a sum of functions. So it's g1 plus g2, so on and so forth, down to gk. So like I've got x squared plus e to x plus sine 3x. Somebody really didn't like me when they assigned that problem. Instead of trying to find something that when I plug it in I get that whole mess, I can consider breaking all those things up and then adding them together again later. So I can think about left side stays the same, but I only look at the first g. Left side stays the same, but I only look at the second g. And I would keep going for however many functions I have on the right side until I get to the end. And so I would like find a solution yp1, yp2, keep going until I get that ypk for each of these simpler problems than the full one I want to solve. With those solutions that I'll denote by yp sub I, because they have different indices for whichever g I picked, then I'm going to get the linear combination of them. Y sub p equal to y sub p1 plus y sub p2 all the way down through that last y sub pk is the particular solution to the full non-homogeneous ODE. And then if I wanted to build the general solution, I would combine this yp, a sum of things, with the general solution of that fundamental solution set. So many words in this section, but when you start doing problems, it all sort of amounts to find all the solutions and add them together. Oh, this page has a lot of words. You might still be writing them down. Next up, I'm going to go over something that I don't think you necessarily need to know, but it's some notation that textbooks can use. So I want to include it just in case. But if you're crunched for time, go ahead and turn off this video, and it's not really going to affect you. But we can think about what's called differential operators. And we're going to denote them by the capital D. And they're going to represent the operation of taking a derivative. So for example, we could have dy dx is dx, or d2y over dx squared, second derivative of y with respect to x, is d applied to dy. Sorry. That first one was dy. D applied to dy is d squared y. And we can do more generally, the nth derivative of y with respect to n would be denoted by d. It looks like power n, but it just means like applied n times y. So for this class of differential equations we've been talking about, nth order linear ODE operator, is going to be given by, we'll call it capital L, and it means a sub n of x applied to the nth derivative that we would normally take of y, plus a sub n minus 1 of x for the n minus 1th derivative, all the way down to a1 of x d and a0 of x with nothing there because we didn't take any derivatives for the thing multiplied by a0. It's just y. And we can use this to represent our ODEs. L operating on y equal to 0 is the same as that first differential equation we talked about when we were forming fundamental solution sets. Or Ly equal to g would be that second more general non-homogeneous case that we talked about for superposition or opening up this section. And so that notation can sometimes be used to show a bunch of different examples of the same differential equation, but we won't be doing that in these videos, so don't worry about this if it doesn't really connect with you.